For most of the history of astronomy, the universe we could study was the universe we could see. Light was the only messenger. If something didn't emit light, reflect light, or block light in a detectable way, it simply didn't exist as far as our instruments were concerned. This worked reasonably well for centuries, because most of what mattered in astronomy, stars, planets, nebulae, galaxies, was bright enough to study directly. Then, in the 1970s, astronomers studying the rotation of galaxies found something that didn't make sense. The outer regions of spiral galaxies were rotating far faster than they should, given the amount of visible matter astronomers could measure. Either the laws of gravity were wrong at galactic scales, or there was a vast amount of additional mass in and around galaxies that simply wasn't emitting any light at all. That invisible mass became known as dark matter. We've spent the subsequent 5 decades trying to map it, indirectly, through its gravitational effects on the things we can see, the way it bends light from distant objects, the way it shapes the rotation of galaxies, the way it appears to form an enormous, invisible scaffold connecting galaxies across vast distances. Hubble, in one of its most quietly significant recent achievements, has just produced the most detailed map yet of one such structure, an enormous filament of dark matter stretching across an almost incomprehensible distance, invisible to every conventional means of observation, detected only through its gravitational fingerprint on the light passing through it. I want to walk through how this was discovered, why it matters, and what it tells us about the true architecture of the universe, an architecture that is, by mass, more than 5 times invisible than it is visible. To understand how you detect something you cannot see, you need to understand a phenomenon predicted by Einstein over a century ago: gravitational lensing. According to general relativity, mass doesn't just attract other mass, it curves the fabric of space-time itself. And because light travels through space-time, light passing near a massive object doesn't travel in a perfectly straight line. It bends, following the curvature created by the mass. This effect, first confirmed observationally during a solar eclipse in 1919, when starlight passing near the sun was measured to bend by exactly the amount Einstein's equations predicted, has become one of the most powerful tools in modern astronomy. When light from a distant galaxy passes through or near a massive foreground structure on its way to our telescopes, that structure acts like a lens, distorting, magnifying, and sometimes creating multiple images of the background galaxy. The amount and pattern of this distortion depends precisely on the mass and distribution of whatever is doing the lensing, whether that mass is visible stars and gas or invisible dark matter. This is the key insight that makes dark matter mapping possible. You don't need to see the dark matter directly. You need to measure, with extraordinary precision, exactly how it distorts the light from everything behind it. By studying thousands of background galaxies and measuring the subtle, systematic distortions in their shapes, distortions far too small to see by eye, but detectable through careful statistical analysis across large samples, astronomers can reconstruct a map of the invisible mass responsible for the lensing. This technique, called weak gravitational lensing, has been refined over decades. And Hubble, despite being more than 3 decades old, remains one of the most precise instruments ever built for this kind of measurement. Because of its extraordinary image stability and resolution, uncompromised by the atmospheric distortion that affects ground-based telescopes. The structure recently mapped in detail is part of what cosmologists call the cosmic web, the large-scale arrangement of matter in the universe, where galaxies and galaxy clusters are connected by enormous filaments of dark matter with vast, nearly empty voids in between. This isn't a new theoretical concept. Simulations of cosmic structure formation have predicted the existence of this web-like architecture for decades, and previous observations have provided indirect evidence supporting it. What makes this particular Hubble result significant is the level of detail and confidence with which a specific filament has now been mapped. Using an extensive survey of background galaxies behind a known filament connecting 2 massive galaxy clusters, researchers performed the most detailed weak lensing analysis yet conducted on a single cosmic filament, producing a mass map with resolution fine enough to study the internal structure of the filament itself, not just confirm its existence, but characterize its shape, its density variations, and its connection to the galaxy clusters at either end. The filament stretches across approximately 60 million light-years, a length that's genuinely difficult to comprehend. For comparison, our entire local group of galaxies, including the Milky Way, Andromeda, and dozens of smaller satellite galaxies, spans only about 10 million light-years. This single filament of mostly invisible matter is 6 times larger than the entire neighborhood of galaxies that includes our own. And the filament is not empty in the sense of being devoid of matter. It contains some visible galaxies, distributed sparsely along its length, embedded within a far larger structure of dark matter that vastly outweighs the visible component. The ratio of dark to visible matter within the filament, based on the new measurements, is consistent with the broader cosmic average, roughly 5 times more dark matter than ordinary matter. But the filament itself, as a structure, is something that no optical telescope, no matter how powerful, could ever photograph directly. It has no light of its own. It exists, in its overwhelming majority, as a pattern of gravitational influence with nothing to see. Here's what makes this discovery genuinely important. Beyond the simple confirmation that dark matter filaments exist, precision tests of cosmological models. The standard model of cosmology, lambda CDM, the same model that predicts the existence of the cosmic web in the first place, makes very specific quantitative predictions about the density, shape, and internal structure of filaments like this one. These predictions come from enormously detailed computer simulations that model the gravitational evolution of dark matter from the early universe to the present day, run on some of the most powerful supercomputers in the world. Until recently, our ability to test these predictions against detailed observations of individual filaments was limited. We could confirm that filaments exist broadly and that their overall properties were roughly consistent with theoretical expectations. But we couldn't test the fine details, the internal density profile, the precise mass distribution, the small-scale structure within the filament, because our observational techniques weren't sensitive enough. The new Hubble analysis changes this. By achieving a mass map with sufficient resolution to study the internal structure of a single filament, researchers can now directly compare the observed density profile against the predictions of cosmological simulations. And the results, published in the associated research, show a generally strong match. The filament's overall mass and shape are consistent with lambda CDM predictions, but with some intriguing small-scale discrepancies that researchers are still working to understand. Localized regions within the filament show density variations that are somewhat different from what the simplest simulations predict, variations that may reflect either limitations in the current generation of simulations or genuine astrophysical processes like localized galaxy formation activity that aren't fully captured in dark matter only. Models. These small discrepancies are not evidence that the standard model is wrong. They're the kind of detailed, high-precision tension that emerges naturally as observational techniques improve, providing exactly the kind of data that theorists need to refine and improve their models. This is science working as intended, better data revealing new details that push theory forward. There's a broader context here that I think is worth dwelling on, because it touches on one of the strangest facts about the universe that often doesn't get the attention it deserves. When we talk about the universe in casual conversation, we usually mean the visible universe, stars, planets, galaxies, the glowing structures that telescopes can photograph directly. But this visible universe, as remarkable as it is, represents only about 5% of the total mass and energy content of the cosmos. Roughly 27% of the universe is dark matter, the invisible substance that forms the cosmic web, holds galaxies together gravitationally, and shapes the large-scale structure we've been discussing. And the remaining 68% is something even stranger: dark energy, the mysterious force driving the accelerating expansion of the universe, about which we understand even less than we understand dark matter. This means that everything humanity has ever directly observed, photographed, or studied through traditional astronomy, every star, every planet, every galaxy, every nebula, represents a small minority of what actually exists. We are, in a very real sense, studying the visible tip of an iceberg whose true bulk lies in regions we cannot see directly and can only infer through indirect, painstaking measurement. The filament that Hubble has just mapped in detail is a direct, tangible illustration of this fact. It is larger than our entire galactic neighborhood. It connects massive clusters of galaxies across tens of millions of light years, and it is, in its overwhelming majority, made of something we cannot see, cannot photograph, and can only detect through the subtle way it bends the light of galaxies far beyond it. I want to talk about why this matters beyond pure scientific curiosity, because I think there's something genuinely significant here about how we understand our place in the cosmos. For most of human history, we believed the universe was essentially what we could see with our eyes, later extended by telescopes, stars, and planets, arranged in patterns that seemed at least at first glance, relatively comprehensible. The 20th century shattered this picture in stages. First, we learned that our galaxy was just one among billions. Then we learned that the universe was expanding and had a beginning. Then, in the latter decades of the century, we learned that most of the matter in the universe doesn't interact with light at all, that the very stuff holding our galaxy together and connecting it to other galaxies across the largest scales is fundamentally different from anything we can directly perceive. The structure Hubble has now mapped is part of the architecture that determined where our own galaxy formed, how it's connected to its neighbors, and how it will continue to evolve over cosmic time. We exist within this invisible scaffold, shaped by forces we cannot see, following gravitational contours that have no light of their own. This is not a cause for existential distress. It's something closer to wonder. The universe contains a hidden architecture, vast, ancient, and almost entirely invisible, that has been quietly shaping the visible cosmos since shortly after the Big Bang. And we are only now, with instruments like Hubble and techniques refined over decades, beginning to trace its outline in genuine detail. So what comes next? The technique demonstrated in this study, high-precision, weak lensing mapping of individual cosmic filaments, is exactly the kind of measurement that upcoming instruments are specifically designed to scale up dramatically. The Euclid Space Telescope, launched by the European Space Agency, is conducting a survey of weak gravitational lensing across a much larger area of sky than any previous study, with the specific goal of mapping the cosmic web in unprecedented detail across cosmological distances. The Vera Rubin Observatory, beginning its decade-long survey of the southern sky, will provide complementary data with extraordinary depth and time coverage. Together, these instruments promise to transform our understanding of the cosmic web from a collection of individually studied filaments into a comprehensive, statistically powerful map of the universe's invisible architecture. The filament Hubble has just characterized in such detail is, in a sense, a preview, a demonstration of what becomes possible when observational precision reaches a certain threshold, applied to just one structure among what theoretical models suggest are millions of similar filaments crisscrossing the observable universe, forming a web whose total extent dwarfs anything the human mind naturally grasps. We are mapping something we cannot see, tracing its outline through the subtle distortions it imposes on the light of galaxies far beyond it. And in doing so, we are revealing the true shape of the cosmos, a shape that exists almost entirely in darkness, holding together the small, bright fraction of the universe that we have always assumed was the whole story. It never was the whole story. We are only now beginning to see what was always there.